All right. Hello, everyone. How are you all doing? Good. Well, I'm not so good. I'm still jet lagged. So if I'm stammering or if I freeze, just give me some slack. Anyways, I'm Ankur. I'm here today to talk about the real-time infrastructure at Uber and how we audit it at a massive scale. I like my presentations to be interactive, so there's a mic there. Or if you have any questions, if I'm going too fast, too slow, just raise your hand and let me know. All right, here's the agenda. So we're gonna quickly look at some of the use cases for streaming at Uber. We're gonna talk about Kafka pipeline, which is the heart of the real-time infrastructure at Uber. Then we're gonna talk quickly about what is auditing, why do we need auditing, and then we jump into the Chaperone, an open source tool which came out from Uber, the version 1, which is already open source for over 1 year, and there's a redesign which has been running in production. Still not open source, but I'll give you a little bit about that, and we'll probably open source it sometime in future. And then we'll wrap it up by talking about the future work on Chaperone. All right, let's look at some of the use cases. You guys might have already heard about real-time processing being a buzzword. For last 3-4 years, everybody wants to be real-time, right? Like most of the companies, they are figuring out how does it fit into their picture, how do they want to do it. But here at Uber, this is bread and butter. If it wasn't for real-time processing, we would not be able to scale and make it an awesome service that Uber is. Let's look at the real basic use case. This is one of the first things that you do, right? As soon as a rider opens up an app, they want to request a cab. The data point goes to the server, and now we have to figure out so many things. We have to figure out who the rider is, where he is, what is the search multiplier over there, how many cars are in the vicinity, what does the traffic look like, and all other bunch of things. All of those real-time data bits go into our stream processing system through Kafka. We do some calculations and spit out the result and say, okay, here's the driver and rider match. And this is the ride which you're going to go with. We also calculate ETA based on a bunch of things, all in real time. Within like a couple of seconds, you see a ride coming your way. Another big application. Who knows Uber Eats here? Oh, awesome. Yeah, if it's a big thing in Amsterdam. I hope it's coming to your city as well pretty soon, and please try it. Uber Eats is another awesome product from Uber Engineering, where we deliver food from your favorite restaurants very quickly. But as simple as it may sound, calculating ETA for Uber Eats is much more complicated even than Ride. In Ride, all you care about is what is the distance and how much is the traffic on the way. While in Uber Eats, you also have to worry about which restaurant is this order coming from. What is the historical ETAs from those restaurants? Are they slow? Are they fast? What kind of dish are you ordering? Apart from the regular distance and speed things. So what happens is all of those data points, along with historical data points, go into our system. There's a machine learning model which predicts the ETA, and it keeps on updating itself as the data is coming in. It generates estimated time for you. Another big one is fraud detection. So like most of the other applications, Uber also has fraud problem. And one of the unique things with Uber is if you take time to figure out a fraud, there's no way going back, because ride has already happened and you cannot do anything about it. So we need to figure out it's a fraudulent request right before the ride happens, which is a couple of seconds. There are more use cases. I can keep going on and on, but pretty much real-time processing is the DNA of Uber. And we don't do it at a small scale. Over years, we have grown to this enormous scale. We're processing more than 1 trillion messages a day. And we process more than a petabyte of data per day. And within the Kafka terminology, we have tens of thousands of topics. I would have said we are among the world's biggest data producers as well as real-time systems until I heard the presentation this morning from CERN. Right? They're probably the biggest. We are nowhere close. But given the real-life applications, we still have an enormous scale compared to many other. Just think about it for a minute. A trillion is easy to say, but it's a huge scale. We're talking about 11 million transactions per second on average. And as you know, not all of the data flows with average. We have slows and ups, and our peaks are much bigger. So we have to build up an infrastructure which can take 10x peaks of this. How do we do this? Again, here's the heart of all of the real-time infrastructure, Apache Kafka. This technology has been very good to us. However, Kafka by itself obviously cannot scale to this humongous level. We had to do a lot of engineering around it to make it scale up to this level. But in short, I would say Kafka is like a lifeline for most of the data infrastructure at Uber. The next question is, what kind of data are you talking about? You're talking about petabytes of data. What exactly are you? What is that data? We use Kafka for pretty much everything. It's used for general pub sub between the services. It's used for stream processing. We already saw a couple of examples. It's used for ingestion into HDFS, S3. It's also used for database changelog. Last but not least, logging, which has probably lion's share of data being produced. And this is important for debugging and figuring out our systems are working healthy or not. Here's how our ecosystem looks like. If you see, we have our Kafka system right in the middle. On the left are all the sources of data, which includes rider app, driver app, all the services, databases. And this is not there, all services produce the data multiple times over. On the right, these are the big consumers of our data. For example, search would be looking at some sort of data points, put it together, come up with a search multiplier, sends it to mobile app. Similarly, Elk gets all the logging data and gives the opportunity for our developers to do real-time debugging. Similarly, Samza and Flink-based stream processing system power our dashboards, real-time analytics, etc. And then we have Hadoop, AWS for long time data storage as well as analytics. We do this enormous scale at a very strict SLA guarantees. We promise about 5 millisecond. It's not end-to-end latency, but it's 5 millisecond as soon as client gives us a message. The acknowledgement goes back to him within 5 milliseconds. And we'll see how that is possible. We give about 4 nines of uptime. We are actually doing much better than that. And then we have reliability guarantees for most of our data up to 4 nines. Some of the critical data like payments, finance, all that is guaranteed 100%. Some data like logging is obviously not that durable because if we have some system issues, we drop messages and we give 99% reliability for that. But most of the data fits into 4 nines. We have multi-DC replication. We have multiple languages that we have to support. And obviously, we need auditing, and we'll talk about auditing in detail. Here's a high-level diagram of our infrastructure. If you see, right in the middle, there's regional Kafka cluster. A regional Kafka cluster is a Kafka cluster for a particular data center. And we have many of those. Let's hold on to that thought for a minute. But that's the center point, and that's where we want to put messages. But a message to reach that Kafka cluster, it has to go through multiple stages. we put REST proxy in front of Kafka. So $1 million question is, why do we do that? Because most of the other organizations which use Kafka, they have no REST proxy. The biggest reason for us is we have hundreds of thousands of clients connecting to Kafka. And if you do any kind of maintenance on Kafka, or if there's an issue going on, you'll have connection thrashing. So think about maintaining hundreds of thousands of those connections. And we have multiple languages to support, which means you have to have multiple Kafka libraries, which was not the case when we started using Kafka. And there are a bunch of features which Kafka doesn't provide. For example, auditing, throttling, and stopping any of the bad clients. So all of that can actually be done in REST proxy. So we put a layer in between, and which has been actually one of the biggest contributing factor, which has made us scale up to this level. Then we have our own client libraries, which are nothing but which does a post request to REST proxy, and each application uses those. We don't use the default Kafka libraries. And once the message starts from application, it is given to our proxy client, it goes to REST proxy, and from REST proxy, it is written to a regional Kafka cluster. From there, we have uReplicator, which is our homegrown version of Mirror Maker. It takes data from regional cluster and it replicates it to aggregate clusters in all the DCs. And all DCs have aggregate cluster, which give you a complete picture of data from all the data centers collected together. So this is the DC1 shows you one complete pipeline for message in a DC. The lower picture also shows you a secondary cluster, which is present in all the data centers. So this is a fallback path in case our regional Kafka clusters were to go down. REST proxies, because we wrote it ourselves, they automatically detect there's an outage on regional Kafka cluster, start writing to the secondary, and from there, the data is replicated back when the outage is over. We have similar thing as local agent sitting on all clients. If REST proxy were to go down, data can be written down and spooled locally, and when the outage is recovered, data is sent back again. All right. So regional cluster is not just one cluster. It's a bunch of clusters, and they depend on what kind of data is being written to them. Why do we do that? First of all, we want to reduce the blast radius of any problem or an issue, because if one cluster is having an issue, you don't want to impact everything. Secondly, each type of data has very different requirements. For example, our logging needs to be very high throughput. You don't want to block, you want to quickly write a lot of data, but it's okay to lose some of the logs. However, a high value data is something which could be slow, but it's not okay to lose any data point because that's dollars. Similarly, time sensitive data like push notifications or search related data, it is very time sensitive. If you are having some issues and if you cannot process everything, it's okay, drop them. But if they're late, they're useless, right? So by having multiple clusters, it gives us an opportunity to tune each cluster for specific requirements, while REST proxy is more or less same for everything. Then we use secondary cluster for fallback. I already talked about it. And then we have aggregate clusters, which collects data from all the data centers and give you a complete picture, so that we have everything replicated from all data centers in one place. All right. Another interesting diagram. Let's look at the life cycle for every data point which is written into Kafka. And this is the key of the scale that we can manage. So as soon as application writes, there's points that as soon as the application writes a data point to our REST client, we get the data in the REST client and we acknowledge. So what we did there is we took the data point and put it into local buffer in the memory, and we acknowledged. This way, we can give a very low latency and very fast response without blocking the application. But the risk there is, if application were to shut down ungracefully, we're going to lose that data point. Right? Then we batch most of the data together for the same topic. We send it over to REST proxy. We do the same thing at REST proxy. We take that batch and we acknowledge right away, even though data hasn't made it to the Kafka still. And then we split the data. We do another sort of batching where we optimize it depending on how we're going to write to different clusters and different brokers. Then we write the data back to Kafka. And within Kafka, same thing repeats. We don't replicate it. We just write it once. As soon as Kafka gets it into the memory, we just return. So what we did here is we did the aggressive batching everywhere. We never blocked the client. And we optimize it for high speed by compromising on reliability aspects. And this is the secret behind low latency, high speed, high throughput system that we have. However, it comes with the disadvantage I've already mentioned, which is anything and everything goes down, application goes down, we lose data. A REST proxy node goes down, we lose data. Regional cluster node goes down or we restart it, we lose data. And that's exactly why we need auditing. Right. So the reason we started thinking about auditing is we used to get this question a lot. Think about it. Somebody provides you a service and says, hey, here's a service which is very fast, but you know what? There is a possibility of losing data. What will happen? Every time you do not see something, you'll point fingers at them, right? You're like, oh, you have a lossy system? Probably you lost my data. And that's what used to happen with us quite a bit. So first problem we solved was speed, and then we started looking at reliability aspects. And this is the question which we would get every day, which is, I wrote X messages, but I only got Y messages. Where are the rest of it? Well, there could be multiple explanations. It is possible that client only wrote Y. They think they wrote X, but they didn't. It is also possible that they hit their quota limits because they were writing too much data very fast, and we actually throttled them, so they violated the SLA. It is also possible that client did a kill 9 on their application and didn't give us chance to flush all the data, which means, it's again their fault, but we need to prove that. Apart from that, it is also totally possible that it is pipeline's fault, and we did lose data. And if we did lose data, we want to find out where the loss was, right? And that's why we need auditing. We also need auditing to figure out what is the end-to-end latency, if we are meeting our reliability goals or not. And auditing also helps us to do accounting as well as chart track. That's where we started thinking about developing a system which can do this auditing for us, and that's Chaperone. Right. So when you think about auditing, so the first problem we want to solve is counting how much messages are going through each stage. So you saw our pipeline. Each message has to go through multiple stages, and they have multiple touch points. First touch point being in the client library, second being in the REST proxy, then Kafka clusters, and then aggregates. So what if we could count the messages for a given time period? What if I could tell, 100 messages pass through stage 1 between 1 and 110? Similarly, if I could count the messages for REST proxy, similarly, if I could count the messages at Kafka, if I could count the messages at each stage for a given time period, I can have a very good idea of how many messages actually started and how many actually made it through all the way. So that's what we did. So that's where the first stage comes in. We ship a counting mechanism in the stage 1 and stage 2, where we created a simple algorithm which can quickly look at all the messages being written and count them. Right. How about the regional clusters? Like stage 1 and stage 2 was easy because they were the code that we wrote, and we could quickly embed the counting code. But Kafka, it was not so easy to embed that code, because otherwise we would have to rewrite. We would have to do a massive rewrite. But again, so Kafka has an advantage. It's a pub sub system, so we could have a service which listens to all the messages and calculate, do the calculations as well, and publish that. So that's what we did. So we created a Chaperone service which can consume pretty much everything coming into the system. So, however, this thing still has a problem. So a message could start at 1 p.m. from the application, but it would reach 1 second later into the REST proxy, and may reach 3 seconds later into the Kafka cluster, and 5 seconds later into aggregates. So if we were to do calculations, there is a time drift issue, right? How do we solve that? Again, if you remember, we control the library, and we basically can embed a timestamp within our messages. So this way, everything is being measured on the creation time instead of it being the arrival time. Here's a very basic picture describing what Chaperone does. So at each stage, we divide the timestamp, which is really an epoch, and take a modulus by 10-minute windows. Right. This gives us, divided by the 10-minute windows. This gives us the bucket that particular message goes to, and within that bucket, we would have a map which would have different topics mapping to aggregated information. So what that this diagram shows here is, within this bucket, topic B, C, and D were the ones who were written to. So this becomes the key, and then the value is what tier this data is being aggregated at, start and end time, what is the count, and then we have some of the latency stats like P99 and average. So we collect this for all the time windows. Then we seal those packets and create an audit message every 10 to 20 minutes, and then we send it over. Right. So this diagram here explains how the audit messaging thing works. So audit library here is doing the counting. So the blue lines show the real data path. The yellow lines show the auditing path. So at first stage, audit library does the counting. It creates the audit message, an aggregated one, and puts it into Kafka as well. So we calculate, count, send it down into the Kafka, because that's the easiest thing to do. Similarly, at stage 2, we do the same thing. Similarly, Chaperone service takes all data, does the counting, sends it back to Kafka. Same thing happens in aggregate cluster. And all of those messages make it through aggregate cluster. That's where the Chaperone collector is a piece which look at the special topic, which has all the aggregate message, all the audit messages coming in, puts it all together, calculates it, and puts it into database. So everything clear so far? All right. One of the key pieces, or one of the challenging pieces, was creating the Chaperone service. So Chaperone service, as you can imagine, it has to read all of those trillion messages and do a calculation. How do we do that? We created a distributed system using Apache Helix, where Helix does the resource management. We can spin up multiple of those workers. And what Helix does is, Helix is like a brain which assigns the work to different workers. And the workers spin up multiple threads depending on how many topics they're managing, and depending on how many brokers they're gonna talk to. And then they do all the calculations and do the same thing that we saw in our libraries and put that data back into Kafka. So I'm making it sound a little bit trivial. This is where meat of the work went in, and you can look at the code, which is open source. But here's the result. In the end, Chaperone can produce the results, which you can go to our UI and easily query. You can say, this is my topic name. I want to search from this time to this time. I will tell you, okay, this many messages were written in REST proxy. This many went into DC1, data center 1, Kafka cluster, data center 2, 3, 4, and total is this. And this many went to aggregate. If you see all these numbers match, and it says, okay, the 100% of messages made it through. We also emit metrics, which you can plot, and this is one of the very helpful thing for us. If you see this top graph, you see all the lines, all 4 lines match up, which shows that all 4 stages had same number of data going through. However, when there is an issue, you'll see a graph like this, where you see that REST proxy client is saying it wrote 82,000 messages, while all other tiers are reporting 53,000 messages. Now from this we can conclude that there was a data loss between REST proxy client as well as REST proxy itself, right? And we can go drill down into what exactly happened, who all lost data. If you remember, we also were collecting data on latency. So Chaperone also helps us figure out the health of the system, how much time does it take on average from data to make it from one end to another. This becomes very important for time-sensitive use cases. So this first version of Chaperone was pretty good for the first iteration. We could scale it up to 250 billion messages per day, which in Chaperone terms, because it looks at everything 4 times, it's 1 trillion messages per day. And we have tens of deployment per data center. And it can do a reasonable good job of calculating latencies. However, it was not good enough, right? As Uber continued to scale, we started feeling that we're not able to operate Chaperone with the ease. First problem was, if you saw the first design, auditing itself was depending on Kafka. So when you're monitoring a system and you're depending on the same system, what does that mean? Whenever you have an issue, you're going to lose your auditing capability as well, right? So whenever you have an issue, you don't even know how much impact that issue caused. So this was the first thing we wanted to get away from. If you remember, Chaperone collector is in the end, which is collecting all the audit messages, and it puts it into a database. The way it was designed, it was a single point of failure because it had a state and it had to get all the messages together. Well, there's an argument we could have scaled it to not become single point of failure, but anyways, this was a design choice at that time. It was a single point of failure. Because our audit messaging are also going through Kafka pipeline, there's a lot of latency which is being added to the audit messages, which was also a drawback. Not a big issue, but it was a little bit of an issue. We started running into scale-related issues because Apache Helix can only manage up to hundreds of thousands of resources, and when we were managing many partitions per cluster, we could not scale it much, which means we had to have one Chaperone deployment per Kafka cluster. And as our Kafka cluster grew, and number of data centers grew, it became unmanageable. And MySQL was always a bottleneck, so our collector can only go as fast as it can write to MySQL. There were other issues as well. Whenever you restart a node, in Chaperone, Helix had a lag in telling the state to all other nodes, which means there could be a double counting. So our accuracy was not that great. How did we fix it? Just like any other engineer, right? Rewrite the whole system. Actually, not so much. So we reused most of the parts that were there. So audit libraries were functioning fine. The first easy improvement was, instead of it writing to Kafka, let's just write to database directly. And obviously, you don't want hundreds of thousands of clients writing to database directly, so we put a web service in between, and audit libraries can just give that message to web service, get an acknowledgement, and web service can in sync write to database. Next pain point, single point of failure in collector. We just got rid of it because everybody is writing to database. So if everybody does the job that collector does, so collector has no job, right? We did the same thing, Kafka services, because there were limited number of nodes for Chaperone Kafka service, we can go and directly write to database. Next pain point was having MySQL bottleneck. We replaced it with Cassandra, which can take much more throughput. And because Cassandra also has multi-DC support, we got that for free, and then we don't have to replicate data in different aggregate clusters. We can just let Cassandra do it for us. So going through the same points again. So decouple Kafka from our auditing. So in that case, we do not have any side effects of Kafka issues. We reduce the delays of multiple staging because we are directly going to database now. We have audit libraries in app and web service, app and REST proxy can go through web service to write to database, and Chaperone started directly writing to database. Got rid of collector altogether, so no single point of failure. Next thing we did is, if you remember, Helix was another pain that I told you about. So we got rid of Helix. So Helix is good for complicated distributed systems where it can serve as a brain, but we don't really need a brain. Our problem was very simple. If we could do a simple hashing of all the topics that we are reading from, that's all we needed. So what we did is we created a Zookeeper-based locking system where if we need 10 workers, we would create 10 locks in Zookeeper, and all the workers will fight for it, and whatever lock they can secure, they'll hash all the topics and figure out all the topics that they need to read from, and they start reading it. This was pretty awesome. This is simple, and this could let us grow a single cluster to monitor all of the Uber data. Another thing is, because we moved away from writing to Kafka model, because all our Kafka services actually writing to database, they can, if there is a contention, if there's a double read, we can resolve that by looking at the database is already checkpointed, use that and see, okay, I'm double reading, I'm not going to checkpoint this. I'll start from the next time bucket. All right. So now we have a single Chaperone deployment per data center. Instead of tens of deployment per data center, it just reduced to one, which reduces the operational overhead quite a bit. And we replaced MySQL with Cassandra, which can handle a lot more QPS and multi-DCs out of box. We were able to get much better latencies because now data goes to, all the auditing data goes to database much faster than it was previously. All right. So what happens if Cassandra was to go down, or if the Chaperone web service was to go down? Well, that's still a problem, right? But guess what? We had already written the code in Chaperone 1 to write to Kafka. So we kept that code. So just in case anything goes down, if the web service were to go down, the audit libraries would figure out that, and they'll retry it a couple of times, and then they'll write it to Kafka, right? Same thing with REST proxy. If database were to go down, Chaperone web service would still be up. It would take all the data from REST proxy and client, and it would write it to Kafka. And same thing with Chaperone service. Chaperone service, because it is doing an asynchronous read, you can just wait for database to come up. So we reused everything that we had to create it as a backup path in unlikely scenario of anything going down. That brings me down to comparing version 1 and version 2. So version 1 was good for what it was, but it was not good enough to scale us to a level further. So we were able to take version 1 to 250 billion messages per day, which is equivalent of 1 trillion Chaperone events per day. And in case of version 2, we are able to scale it to more than 1 trillion messages per day for Kafka, which is equivalent of 5 trillion Chaperone events. Earlier, we had one deployment per Kafka cluster. Now we have one deployment per data center. Latencies are much better, and it's easier to operate. And we're saving a lot more resources. It's much more efficient. So again, to summarize, Chaperone is our in-house auditing system. It has been running in production for 2 years. Version 1 has been in production for 2 years. Version 2 has been in production for about 9 months. Version 1 is already open sourced. Feel free to try it out if you're using Kafka. We also have a blog which tells you more about details of how it was developed. And we will be working on open sourcing version 2 whenever we can get some time. And again, some credit of this whole design goes to LinkedIn Engineering. They published a blog sometime back, and which became the inspiration of our Chaperone. So we're not done yet. Even though we can handle this much scale, but we can take Chaperone a bit further, and we already have some prototypes working on this. So this was all about calculating if we had data moving from one end to another end. How about the duplicates? We still don't handle duplicates very well. We're working on it. And I'll talk about it whenever it's ready. Another thing that we're working on is, because we're looking at each and every message, we can do much more than counting. We can look for interesting patterns like fraud, issues, or sensitive data getting into where it should not be. And we already have a prototype for that as well working. All right, that's all I had for Chaperone. And I think I'm a little bit early. This leaves us 10 minutes for questions. Thank you.
I'm not sure to get how you match your time bucket, because you can have clock synchronization problem between your nodes, and you have latencies between your nodes. So one bucket of 10 minutes is not exactly the same of the other bucket of 10 minutes from another service.
Yeah, so
it's not 100% count exactly.
Right. So the question here is, again, the time drift problem, right? So the latency is between one stage and another stage. So that's what I said. So the way we do it is we embed the timestamp within the message, right? And then we can use that timestamp, right? Then we can, even though it arrived a minute later, we can still put it into the old bucket where it belongs. Any other question?
How did you manage for the web service to not be a sloth? because there is a single web service for all your application in a data center.
Mm-hmm.
So how can it not
So
be a spot?
it's a stateless web service, which has multiple hundreds of nodes actually spin out, right? And when you write a message, it stores its state. For example, which topic does it need to write to in Zookeeper? So it pulls that whenever a new web service comes up, right? It interacts with Zookeeper, figures out where all the clusters are, and then you keep writing data. It knows where your topic belongs to and just writes over there. Right. So it's still stateless. However, it's not completely stateless. There is that state which is maintained temporarily before it is being written to Kafka. So that's something, obviously, that's something I've called out. Yeah. Any other questions? All right. Thank you all for coming.